Yeah, Dylan.
I may have done it wrong, but like, I feel like I don't know how there's like one.
We can take a look at that after. This isn't going to take the full time. I'm going to take like about 50, 60 minutes on this, and then the rest of this time will either be working on the study guide if you hadn't finished it yet, or there's a new classwork for Combinatorics that you guys can work on as well. But I would be more than happy to take a look at that once we're done, for sure. All right. So this is Combinatorics. Combinatorics. And we're going to start with what is fairly basic, a fairly basic kind of counting problem. You guys probably already know the methodology. Like if I were to ask you how to do this, you'd probably know it. I want to build up an intuition of why this must be true, though. So we'll go a little bit, that might feel a little bit slow at the start. But hopefully by the end, we're able to do some pretty cool stuff that we maybe haven't seen yet before. And we're gonna, by the end, so by Wednesday, we're gonna have looked at how this kind of relates to some seemingly very, very different, very, very disparate realms of math, which is super cool. All right, so combinatorics here. Let's say we have, this is kind of like the prototypical counting problem that you're going to encounter on like the ACT or the SAT or just in general in the wild. You've probably seen this a billion times before already. Let's say we are trying to pick an outfit. And for this outfit, we have three different components. We're going to kind of generalize this methodology here in a little bit, but we can pick out a shirt, we can pick out pants, and we can pick out shoes. Let's say for the purposes of this, we have 5 different options for a shirt. We have 3 different options for pants, and we have 4 different options for shoes. The question is, how many total possible outfits could we arrange from these types of clothes that we are given here? All right. And again, I'm sure that many of you already know exactly what to do. That's great. That's awesome. Let's start with a small case and work our way up to kind of this slightly larger problem. And then the extrapolation will be, okay, we could do this as many times as we want for as many slots as we want. And we're going to consider kind of what this is trying to get across and why I've kind of represented this in a slightly more abstract way than thinking about picking out outfits. All right. So what we're going to focus on first is let's think about the number of ways that we can create a shirt-pants pair. So the number of ways we can match the shirt to pants. For this, let's say that we said we have 5 shirts. So this will be like A, B, C, and D, C, D, and E for our shirts. That's funny. Shirt C, shirt D, and E. And this will be, we'll say pants 1, 2, and 3. The brute force way, where if you don't really know the math and you see this question on the ACT and you feel like you have enough time, would be to literally just go through and count the number of different possibilities here. And we certainly could do that with a small enough sample space that's not wholly unrealistic. So this is kind of why this is a counting problem, is we could solve this problem by constructing these pairs and then counting the number of unique pairs that we can construct. Of course, ideally we'd have a faster way, and so we're going to shortcut this, but let's start by manually making these pairs. And the way that we're going to manually make these pairs, we're not just going to randomly go through and say, okay, we'll do shirt A and pants 3 and shirt C and pants 2 and shirt D and pants 1, and then just like hope we don't miss one. We're going to be very, very methodical about how we do this counting. Let's start with thinking about the number of pairs that we can get from shirt A, and then the number of pairs that we could get if we use shirt B, and then shirt C, and so on. We're going to fix that first kind of slot. We're going to say, I know going in that I want to start with shirt A. How many outfits can I generate if I start with shirt A? I know that I want to start with shirt C. How many outfits can I generate with shirt C? And what is the answer? How many outfits can I create if I know I'm starting with shirt A? 3. I can pair shirt A to pants 1, A to pants 2, and A to pants 3. There are 3 options of these shirt pants combinations that I can create here. All right. How many different options do I have if I fix shirt B instead, if I'm looking at shirt B instead of shirt A? Also 3, and it's a pretty similar 3, right? It's B to pants 1, B to pants 2, and B to pants 3. And in fact, with all of these, how many different outfits am I going to get if I fix the shirt to be a particular shirt? So for each shirt, how many different outfits can I generate? It's going to be 3 for each one. So 3 for shirt C, 3 for D, and 3 for E, for a total number of shirt pants combinations of how many? 15. Very good. Which we could have arrived at by doing 3 plus 3 plus 3 plus 3 plus 3. But what's maybe the easier, faster way to do this kind of repeated addition here? Yeah, it's the number of shirts times the number of pants. This is 5, which was our number of shirts, times 3, which was our number of pants. So 15 possible pant-shirt combinations, which we can arrive at very, very simply by just multiplying the two together. Right? Each shirt can create 3 outfits. When we're looking at just these 2 variables, we have 5 shirts total, 15 total outfits. Okay. I could just tell you, oh, by the way, we can do this over and over and over again, and that's fine. But let's actually see that. I want to think now of a shirt-pant combination as kind of acting like one piece of my outfit. Right, so we kind of do have these like separate pieces, but I could also think of a pair of pieces as being like one component, and I want to pair that component with a set of shoes as well, right? So we could think of our shirt pant combinations, all the possible ways that we can create shirts and that we can pair up shirts and pants. We could think of shirt A matching with pants number 1, shirt A matching with pants number 2, and we could go on and on and on until we end up with shirt E matching with pants number 3. And if I'm considering all of these combos, these shirt pant duos, how many options did we say we had for these? We said we had 15 different shirt pant duos. And then for shoes, we have several shoes. We can think of shoe, maybe like alpha, shoe beta, shoe gamma, This is just so that I'm not overusing like the various things. You could do shoe A, B, C, and D here as well. That's totally fine. Shoe, delta, whatever. You get the picture. All right. So for our first shirt pant combo, when we bring shoes into the mix, how many different outfits do we get per shirt pant combo? 4. 4 different possibilities. How many different shirt pant combos did we say we have? 15. So we have 15 combos. Each one gives us 4 outfits. We have a total of 60 outfits. Remembering that that 15 came from the fact that we had 5 shirts combining with 3 pants. The very, very simple way that we can do this counting is we can take the number of objects in each position and we can just multiply them together to get the total number of possibilities. And you could do this with, we could add socks, we could add hats, we could add whatever. We can add as many slots as we want. And again, the end result is just taking the number of options that we have per slot and multiplying all of them together. Now, abstractly, so kind of taking a step back, the concrete example is what's going on here with shirts and pants and shoes and outfits and all that fun stuff. But a really nice way to kind of think about what we are doing is we're kind of creating a list here. We have these spots that we need to fill. The first spot, the second spot, the third spot. For our example, for our concrete example, first spot corresponded to the shirt that you were wearing. Second spot corresponded to the pants that you were wearing, so on and so forth. And we are trying to figure out the number of ways that I can fill a particular spot. Or we're not figuring it out, but that's part of what we're given, right? I have 5 different shirts that I can wear. I have 5 separate objects that can go into spot 1. There are 5 different outcomes that I can see from spot 1. All of these are the same idea communicated at varying levels of abstraction, or maybe with slightly different spins on them. All right, so 5 shirts could have been 5 marbles from a jar, or 5 whatever. Like there are various ways that we'll see this. We'll look at some other examples, actually quite a few very, very different examples than just like this, like thinking about number of outfits. But there is something about like arrangements here that's happening. There's something about filling out these slots with thinking about like the number of possible ways that we could put things into the slot. A couple of things like that that we're going to kind of continue to expand on as we go. But before we do that, take a quick pause. Any questions with kind of our basic setup for what we do to count these spots? Yeah. Yeah. 10, 15, however many, yeah. Or just like going through and multiplying. Either way is fine. If you can do multiplication in any order that you want. I would probably just say go ahead and multiply them all. It'll work multiplying them all. And realistically, what this would be is you're gonna take your calculator and you're just gonna and you can do it all at once, and that's totally fine. Yeah, I mostly did the grouping just to convince us that in fact the way we would go from like ordering 2 objects to ordering 3 objects is not very different than how we ordered 2 objects. You just keep multiplying over and over again. So this was more demonstrative than it is like what I would actually do to solve. Yeah, good question. Other questions here? Sorry, a little bit of a kerfuffle. Okay. So let's take a look at, we've got a couple of other examples that we're gonna play around with, that we're gonna run through. We're gonna take a little bit of a look at like how you would actually use these for things like finding out probabilities, tiny little look. And then we're gonna mess around a lot more with this idea of like ordering and filling in these slots and other ideas that are very similar. Okay. So let's consider a new situation. It's going to be a little bit of a weird, again, kind of abstracted situation, a little bit contrived, but that's okay. We're going to do a couple things simultaneously. We are going to flip a coin, and we are going to roll 2 dice. And the question that we want to ask is the number of possible outcomes that we can get from rolling those 2 dice while also flipping a coin. So we have essentially 3 different actions that can occur. Kind of. Well, this is how I would think about them. It's an okay way to think about them. You could think of maybe rolling the 2 dice as being like one action. And that would have its own affiliated kind of combinations. But for now, we'll think of these as like 2 separate objects, and we're maybe rolling 1 dice and then rolling another. That's totally fine. For my coin, how many different outcomes is it possible for me to have with my coin flip? 2. Okay, so I can either be heads or tails. We're gonna assume that our coin is not landing perfectly on its edge. Although I think some interesting math has been done around like that as a possibility. For our dice, we'll assume we're using just like a standard D6. How many different possible outcomes? There are 6 possible outcomes, and I'm actually gonna do the dice color a little bit different here for reasons that we will see. So 6 possible outcomes for D6. And then for our second dice, also a D6, also 6. For a total of 2 times 6 times 6, 72. I'm going to say in quotations here, different possibilities, outcomes. Can anyone figure out why I have put different in quotations? What might be a little bit misleading about this number 72? This is a tricky one. This is where combinatorics gets to become a really big headache, which is, entertaining and fun and all that. Yeah, it has to do with the die. Very nice. So this 72 is not going to consider rolling a 5 on dice 1 or die 1 and a 6 on die 2 as being the same as rolling a 6 on die 1 and a 5 on die 2. So we could imagine in this world, we have some way to distinguish between the outcome that we get from the first die, the outcome that we get from the second die, and that for these purposes, that creates a different outcome. But we do have some kind of potential overlap here, where maybe in a more refined world, what we would really want to be considering is, okay, but how many different ways could a 3 and a 4 come up where it doesn't matter which die it comes from? Because that's generally actually what you care about, right? You normally don't care about the fact that it's the die on the left that's giving you the 2 and the die on the right that's giving you the 5. Generally, it's what those 2 numbers are, independent of where they're coming from, that actually matter. And so we get a little bit of complexity there. So these are different outcomes, mostly coming from the fact that, yeah, it's totally possible to end up with a 1 on one die and a 2 on the other, and that is treated as a fundamentally different outcome than a 2 on the first die and a 1 on the second one. And whether we want that or not is going to depend on the type of question. For this particular demonstrative, we'll assume that we want the outcomes of the die to be different. We'll assume that a 1 and a 2 is different than a 2 and a 1. And that gives us this 72 that we see here. All right, let's modify this ever so slightly. Let's say that you have a wager with some friends for a particular set of outcomes, and you're trying to figure out how likely this kind of set of outcomes is to occur. We know all of the total possible outcomes. Again, we're going to assume that the blue die and the red die are distinguishable from one another, and we're going to set some restrictions on them. Let's say that we make a bet here. And the bet is that the blue die is either going to land on a 1 or a 3, and that the red die is at the same time going to land on some even number. Right, let's try and figure out the number of different ways that we can win, the number of winning combinations that we have here, and we'll see, can we use that to figure out how likely this scenario is to actually occur. For our coin toss, does our coin toss influence in any way, or do we care really in terms of like whether we're winning or losing about whether the coin comes up as heads or tails? No. The winning and losing condition was something that we are only applying to our die, and so our coin is still allowed to be either heads or tails. So the coin itself here has not changed. For our blue die, which we said could either be a 1 or a 3, how many different outcomes do we want to see? We want to see 2 of the 6 possible outcomes. And to land on an even number, how many possible outcomes are there? 3 possible outcomes. Multiplying these all together, we get that there are 12, we'll call them winning possibilities. We can already kind of see that this is a fairly powerful, like our ability to calculate these really, really quickly is fairly powerful. This would be a kind of annoying thing to count. The sizes of the numbers aren't too hard to figure out. They're just like matching the like 1 to the 2, and then 1 and 4, and then 1 and 6. All that. Yes, absolutely. Okay, so if I want to know whether these are particularly good odds or not, and we're not really going to focus too much on the probability side of this. We're mostly going to be generating the sample spaces from what we're going to be doing. We're going to be focusing on the counting problems rather than how we might use the counting problems. But the basic idea is our chance to win is there are 12 winning combinations out of a possible 72 total outcomes. Simplifying this down, we have a 1 in 6 chance to win. Which there are several ways that you can interpret this, but you would expect to win about 1 of every 6 attempts, assuming everything is fair and even and nicely distributed, assuming each of these outcomes are equally likely to occur, uniform outcomes. And when they're not equally likely to occur, then you end up with another headache, and statistics is just such a fun little ride for all of that. All right, questions with our counting problem so far? All right, let's take a look at an example. I'll give you guys a couple of minutes to think about how we might approach this one. Let's look at some phone numbers. Each phone number has, for the most part, we're going to think of phone numbers as having 10 digits. We've got the first 3 digits, which are our area code. Followed by 3 digits, followed by 4 digits. We'll assume for these purposes that we know the area code. Let's figure out the number of different phone numbers that we can generate under a particular area code. So we'll say we know that we are looking for the number of possible 901 phone numbers. Take a second, take a stab, figure out what you think, what would you do in order to calculate the total number of possible area codes. The follow-up here is going to be how many possible just phone numbers in general are there. So if you get through with the area code one very quickly, then that's just a very quick adjustment. But take a moment to consider, what would we expect this to be? Or maybe constructing what would our methodology be for approaching this. Yeah. Mm-hmm. All right, so let's take a moment to consider what we've got. How many options do I have for each of my slots here? I haven't really put a restriction on anything, so we'd expect to have the same number of options. How many options do I have for each of my spots? 10 different options for each. How many different slots do we have for our phone number that we're trying to fill? 7. And so is that going to be 70? Nope, that is going to be 10 times 10 times 10 times 10 times 10 times 10 times 10. This is going to be 10 to the power of 7, which means that for a particular area code, there are 10 million possible phone numbers. Which is a fair number. It's also why area codes exist. Before, we had our original 7-digit phone number. And then as soon as the number of active phone numbers surpassed 10 million, we needed more. We couldn't get away with just having the 7-digit, just the 7 digits. And so using the area code to kind of extend it. If we don't fix our area code, if we allow that to be whatever it wants to be, what is our new values? This is like with area code fixed. If I don't fix my area code, what is my total number of possible phone numbers going to be? Ten to the what power? 10 to the power of 10, which is 10 billion. Phone numbers, 10 billion possible phone numbers. 10-digit phone numbers, I guess we should say. Which actually does create a question. Obviously, there are less than 10 billion people on the planet. But if eventually we reach that 10-digit, that 10 to the power of 10, if eventually there are that many active phone numbers, then phone numbers will need to be a little bit longer. Now, that being said, if I were to even add a single digit to the phone numbers and create like 11-digit phone numbers, that would mean I have 100 billion different possible phone numbers. So even adding one digit would be enough to generate a full magnitude more of, again, these like possible phone numbers. So it wouldn't need to change all that drastically. And in fact, we do have the country code that sits out in front that people often forget about. So like there is this slot right before here that tells us that it's 1 because we are the US and Canada or whatever that particular larger area code is. And so actually we probably do have closer to something like 100 billion possible active phone numbers here that we will not really approach anytime soon. All right, let's do something contrived. This is going to feel very silly and not really seem like it has a point. The analogy that we will be working with here, we can think of a couple of different, we'll talk about this more, why this situation actually comes up more than what I am going to portray it as. Again, it's going to be like a very silly extension of this phone number problem. And we're just going to kind of run with it. Let's say I want to pick a phone number. We'll say it's a 10-digit phone number, so we won't worry about that number that sits out in front. Pick a 10-digit phone number that does not repeat any digits. So we have our area code, which we're not going to fix. We'll assume that our area code is part of this. We are trying to figure out the total possible number of ways that we can construct a 10-digit sequence that that doesn't repeat any digits. So again, take a minute, think about how you would do this. You want to try and calculate it yourself. Give it a stab. How would we do this? What's going to be different about what we did here versus when we didn't care about repeating digits, right? Where 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 was definitely a valid solution for our first one now would no longer be. I mean, you could use 90 or 1, but if you use 901 as your area code, then a 9 isn't going to show up anywhere else in your phone number, nor a 0, nor a 1. So that you would have to use the other digits instead. All right, let's take a look at this. Looking at our first digit, and it doesn't need to be the first digit. We could go through, pick any digit. We could work from back all the way up to front. That would be totally fine. We could work really randomly and just like fill it in like very, very arbitrarily. That's totally fine. But for the first value that we fill, the first slot that we fill, do we have to worry about running into any repeating values, like from the first thing that we're going to fill in here? No, there's nothing else for it to contend with, right? So thinking about filling this first slot, which again could be any of these slots, but again, just thinking about filling one of them, how many different options do we have? We have 10 different options for our first slot here. And we'll go ahead and say, pick one randomly. Maybe this is a 3. Who knows? All right. We move on to another slot. Again, it doesn't have to be the second slot. It could be any other slot that we are filling in. But the next slot that we fill in, we are again looking at the number of things that could go in there. How many possible outcomes, how many possibilities do we have for things that could go into the second slot that we fill? 9 different possibilities, because we have already used up one of them, right? 3 is no longer on the table, and so we drop our number of total possibilities down to 9. Again, it doesn't need to be the second slot, but I'm partially trying to do this in a way that will visually make a point. We'll say that that fills with a 0. How many possibilities are we going to have for our third slot that we fill? 8. We've used up 2 of the 10, and so we have 8 remaining options left. How many for the fourth slot? 7, and then 6, and 5, and 4, and 3, and 2, and then finally 1 option for our very, very final digit, kind of what's called pigeonholed into that last spot. There is not any really freedom of choice for where that one can be, that last one can be. Okay, and we say we arrive at our final answer. We have the number of possibilities, the number of different kind of ways that we can fill a slot. We would multiply each of these together, 9, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 2 works out to be like 3 million and something. A lot of different possibilities. Of course, a lot less than 10 billion. And in fact, 3,628,800 would be the exact value that we are looking at. But again, this was a fairly contrived example, right? This idea of looking at such a oddly specific phone number doesn't really feel like it has a lot of utility to it. But actually, this idea of ordering where you're not able to reuse things that you have already used is something that comes up all the time. For instance, let's suppose that we wanted to, and I'm just going to use this because this is what had always been relevant to me in high school and college. Let's say we have a tennis team that has 6 players. And we're trying to figure out, well, we're going to be playing against this other school. They're going to bring 6 players as well. And it's actually pretty important to decide who's playing court 1, who's playing court 2, court 3, court 4, court 5, court 6. There is something fundamentally different about bringing one player at first and bringing one player second than switching the 2 of them, right? It changes the outcome. It's a different roster if you switch your first court and your last court. It ends up being a completely different set of outcomes there. So in this case, the order of this kind of sorting really matters. We see it with phone numbers, right? 901 is a different area code than 109. The order in which the numbers fall is something that actually is really quite important. So when we are doing this, we can imagine how many different players on a team of 6 How many different ways could we construct this roster? Well, for the number of players who could play in the court 1 position, we have 6 different possibilities. And so we pick one of them, preferably the best one. Best player goes in for court 1, and then we move on to court 2, and we say, okay, how many players do we now have? How many different options do we now have for putting a player on court 2? And we are now down to 5, because the player on court 1 can't play on both court 1 and court 2. You can't fill both of those roles as much as I'm sure many teams would like their court 1 player to do. And so it's actually very important for ordering people. You could also imagine a situation where maybe I have exactly the number of desks as I have students, and I need to figure out the number of different seating arrangements that I can generate. A student that sits down in a desk, whether it's the first desk, whether it's a random desk, it doesn't matter. They have a certain number of options. A student can fill one of those slots. In fact, any of my students could fill that slot. But as soon as one student has sat down at a desk, that as soon as that slot has been filled, that student can't then also sit down at another desk. And so the total number of possibilities gets reduced. Again, this is a very contrived way to do it. We're just arbitrarily saying that I don't want to reuse things, but certainly we could imagine plenty of situations in which it either would not be desirable to use one of our objects more than once. Of course, objects, mathematically, people, whatever. It's not desirable to do so, or where it's just literally impossible for something to be in 2 places at once. These slots can be physical things, like physical places as well. And we can't occupy 2 locations at the same time. This has a fancy math term. Mathematicians, again, it shows up all the time. We're going to see some very crazy places where this becomes very, very relevant. This is something that gets used a lot, all over the place in combinatorics. I am not going to write out 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 when I want to do this operation, if it's showing up this much, right? That's ridiculous, not going to do that. And 10 is not that big of a number. If I took 100 times 99 times 98 times 97, blah, 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 all the way down, that would suck. And we're not going to do that. Instead, what we are going to do is we express this idea of starting at the number where we are and multiplying by each subsequent natural number all the way down to 1 with what is called a factorial. This product here is the same. You might see this written as 10 with an exclamation mark afterwards, which is the factorial symbol. So 10 factorial is very simply 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. All right, questions with our factorial construction? All right, let's take this tennis example and let's extend it. It could be chess if you wanted it to be. Would you prefer a chess team that has 6 different boards to fill? Be anything. We'll switch to swimming once we work to something else, but that will have something actually fundamentally different as part of it. So let's say again, we've got this tennis setup that we need. We want to bring 6 players to play this match. And again, with tennis, it's actually pretty important that the first player that we select Like there's a big difference between being selected first to play on court 1 and being selected fifth to play on court 5. There's something fundamentally different about the order of being chosen to go to this match than if it was just like, oh, you're going and that's all that matters. We'll look at those examples later. But for now, order is important. Before we said our tennis team had 6 people and there were 6 slots to fill. The phone number example is a pretty nice example of this, where we had 10 different digits and we had 10 slots to fill with those digits. And so we got 10 factorial. That's really nice. Let's make our team a little bit bigger. Instead of 6 players for 6 slots, we're going to say we have 10 players for 6 slots. So we still have 6 different people who, or sorry, not 6 different people, 10 different people who need to be assigned to something. Over to the left-hand side of our line are the people who are playing. And to the right are the people who are not playing. Okay. How many different ways can we fill the first playing slot? How many? So how many total possible players do we have that can be assigned here for our team of, what's our team size? 10. So we have 10 possible players who can be playing. And so this one would have 10 different players who theoretically could be on court 1 here. All right, we assign that player. They're on court 1. How many different players are therefore on, do we have to choose from for court 2? 9, and then 8, and then 7. And then it looks exactly like, oh, did I mess up the number of slots? I can't count. That's fine. A counting lesson where the math teacher can't count. That's good. That's really good. I understand now where 5 came from. Okay. It's because I can't count. Cool. So 5 different slots here, and then 4, 3, 2, and 1. Okay, so 10 factorial is what it looks like. To the left of our line, players that are playing. We said that order matters, right? There's a fundamental difference in being in the first slot versus being in the second slot versus being in the third slot versus being in the fourth slot. So over here, we have that order matters. But if we're thinking to the right-hand side of our line, does it matter who didn't get picked to go play first? Like if we have player A, B, C, and D, does it matter that player A got told you're not going to this match before player B got told that they weren't going to this match for the practical intents and purposes of designing this roster? No. So we have a side here where we could mix and match that 4 factorial, right? This right here, what we see here is 4 factorial, and it's 4 factorial that doesn't matter. Where we can arrange these 4 players in any order we want, and it doesn't actually affect the outcome of what is happening, right? If you get picked, then it matters the order in which you get picked. If you don't get picked, all that matters is that you didn't get picked. And so in actuality, this 4 factorial of not mattering, of not contributing to the total number of relevant unique rosters would get in some way left off, and the relevant piece of information here is going to somehow be contained, or not somehow, but will somehow be communicated through this product here, not counting anything that's to the right of the line where we don't care about order, where we could mess around with those or like those arrangements all we want and nothing would actually change. We're going to come back to this idea. We're going to stop here. We're going to come back to this idea of what is called a permutation on Tuesday. So test on Monday, revisit this idea on Tuesday. And we'll start with this kind of idea of the significance of having a portion of your selection that has been ordered, a portion that has not been, and what we need to do to mathematically resolve that. In the meantime, we've got about 30 minutes left, a little bit less. There is a Combinatorics classwork that has been posted. As soon as it starts talking about like, I'm actually not sure. As soon as you click the view an example and it starts talking about permutations, you can stop. I don't know exactly what number that is. But you have that you can be working on. There is the study guide. If you did not have an opportunity to finish it, that would be a really good thing to work on. I have also posted the late work password for the 6.3 classwork if you did not have an opportunity to finish that. So working on one of those three things for the end here. And I will be fielding questions, probably mostly referring to the study guide, but of course to any of this.